So our last speaker from this session is Alessandro Caproni. He's a software engineer at ESO, the European Southern Observatory, and the technical leader for the integrated alarm system. That is the system that is going to be introduced by him right now. Okay.
So, hello, good evening. So I'm going to talk about the integrated alarm system for the Alma telescope. Now that Alma Observatory is in operation since a few years, we have now time to look into the problems. And one of the problems is actually the fact that the control software of the Alma Observatory, the Alma Common software, alarm system is actually not enough. There are several problems about that. We are not going to talk about this, but in particular, the current alarm system does not allow to see all the alarms that are, or the problems that appear in the system. In particular, the operators that need to solve the problem now are developing their own panels. So in the control room, there are a set of different panels with their look and feel, colors, sounds. And when there is a problem, the operators has to look at the right panel. They have to find where the problem is and so on. And also one of the big problems here is that not all the alarms are visible in the array in the online control software. So we have to integrate and get alarms from different point of view. Basically, the goal we want to improve at the end the efficiency of the telescope. So we have started. Okay, we have started. So this is high-level pictures of what we want to have. Basically, we want to monitor more hardware system. Here is the online software, but for example, there can be the network or the power plant. They have their own control software systems, and we want to get alarm and monitor points from all these hardware systems and route them to the integrated alarm system that will elaborate them and present to the operator in the proper way so that can easily understand where a problem is and fix. We have done a study about that with the help of a software engineer responsible for the alarm system of the European Space Agency. And we came all together to the conclusion that we can model our system with a graph like that is modeling from the point of view of the alarms, not a modeling of the hardware or the components. Each of these nodes can be in a nominal state when it's green, or can be in an alarm, and we can propagate up to the top to define if something is at the end in alarm or not. If we can then map the model to the two display elements, here they are displayed as boxes, but they are actually more sophisticated GUIS, then we can provide the operators with a proper interface that it can easily understand the problem. When an alarm like this is in red, the operator is in principle able to press over here and show a more detailed view of an equipment. So the architecture of the integrated alarm system is based on the DASU. You can see we have in this example we have one DASU for each for the three examples of hardware system. I have the water system, the power plant, and the Alma array here, and they receive the inputs from the monitored control software. The same inputs can be shared by more than one if it makes sense, if the input, for example, a power line is affecting more equipments, and they produce an output that will be in a nominal state, that's the green state, or if there is an alarm, it can be in an alarm state. And the output of the power plant, so the alarm generated by the power plant, can be in turn routed to other DASU elements if they need to know this alarm state. So each DASU is composed by several computing elements. So basically, start from the bottom, we have here the monitor points and alarms that are produced by the various monitored system. We can have as many DASU as we want, so we can partition the inputs. But these inputs here are the ones that are produced by the monitored system, so they have the monitor system or the control system data structure. So we need to convert all these monitor points and alarms into values that can be digested by the DASU. This is only a logical view because the conversion layer can be in a different place. But the important thing is that what is here is something that our integrated alarm system can understand. Then these inputs are routed by the DASO to the computing elements, and they are elaborated in order to produce an output that you can see here. So, for example, in this case here, the computing element 3 is generating an alarm, as well as the computing element 1, but the computing element 2 is not in alarm state. So the power of the transfer function, that is what is elaborating the input in the computing elements and generating the output, is that it can elaborate the inputs and decide if an alarm is really an alarm or is something that must be hidden to operators. For example, the computing element 4 is receiving here 2 alarms, but is not producing an alarm in output. This is typical cases, for example, we are monitoring a device that is under maintenance in a certain moment. This alarm should not disturb the operator in the control room, so we can hide. The transfer function in the current implementation is, so this is basically now developed with Java and Scala. And the transfer function at the present is, you can pass basically a Scala or Java class to implement the transfer function. It is loaded at runtime, it's read from the configuration database and loaded at runtime and associated to a proper computing elements. The transfer function, okay, the integrated alarm system will provide the most common transfer function, like for example, if you have, for example, if you have a temperature with a threshold, this is something we can provide. But the power of this transfer function comes where computing elements is actually dealing with many input for which we cannot define a transfer function that easily. And in that case, this transfer function must be thought together with the operators and the engineers that know the system. We are thinking to implement this also in other languages. For example, Python would be nice because the operators knows very well Python, but there are other options actually under investigation. So at the end, all this chain of computing elements as the last one, the computing element 7, that is generating the output of the entire distributed alarm system unit. So just go briefly around this. Everything that runs into the integrated alarm system has an identifier, starting from the inputs that comes from a remote system. This is, sorry for the names, this is a temperature coming from the Alma common software. This is the converter and the converted value, and we are composing the identifier to know basically the history of all the elements. If you see this last one, for example, it says that the temperature that has been generated by ACS somewhere is being converted by the dB conversion, and is also and now is available in the system. This allows us to easily debug the system because we know an item and we can know exactly which part of our alarm system has dealt with it in the Okay, communication with the monitored system happens through a backstage database, as we want to decouple the monitored system from the integrated alarm system. In particular, we don't want to affect the monitored system by problem in the backstage database or the integrated database. So they are basically, there is we call a plugin that is basically collecting data from the monitor system and pushing data into the backstage database. If the backstage is not available, the plugin does not do anything. The integrated alarm system, so it swallows the errors basically. The integrated alarm system provides a plugin that basically deals with collecting the data and sending the data to integrated alarm system, and the developer should only deal with a particular control system that they are monitoring. So it should in principle not be a big deal to produce new plugins. We have identified many scenarios in this because the monitor system we have are very different. We have some that are on which we have full control because they are developed in-house, like the Alma Common software or the weather station, but we also have control software that are proprietary on which we do not have many control. We have seen that some of them provides an API to get monitor point and values, but some others does not. So in the worst case, we have probably to get the monitor point values, in the worst case, parsing the logs. Okay, so this is basically the data flow we have. So this is a monitored software, for example, the power plant. There is the plugin running here or somewhere. It's not very important. It's collecting the data and is pushing the data into a queue, a temporary queue. This data here is still in the format of the monitored system, but there are some workers here that takes the value from the TQ and convert into the values that are accepted by the integrated alarm system. And these values are then routed to the computing elements and the DASU. And the output of the DASU goes in the same queue. So basically, the data structure is used for both cases, the monitor points taken from the monitored system and those produced by our alarm system. And then these values are also sent to a Cassandra long-term database and used for technical and operator GUIS. We have also an hash queue to access the data with their identifier, but this is mostly for the technical part. The backstage database is based on the Kafka framework, on the Apache Kafka framework. Okay, this is a more detailed view or different view. We can, thanks to Kafka, we can in principle partition and have more temporary queues, and we can have more IOS queue and converters and publishers. This comes basically, or does not come for free, but is easy to have with Cassandra. Okay, this is the bigger overview of the system. This is mostly to show that we have different control systems that they have to get the data from the plugin has to take the data. For example, the common software where we have full control, we can in principle have an Alma common software client or even a component that is getting monitor point values and sending them directly to the backstage database. We can have a process running in the same server if we can control it for the weather station. But in the worst case, the plugin could also run in whatever computer and poll the data if we don't have control over that, and everything goes into the backstage database. From the backstage database, then the values are routed to the server and finally to the web server that is where our web server is running to send the data to the GUIS for operators and engineers. Okay, this is a schema. So basically what I want to say here is that the web server, like the core, is not connected directly to elements of the integrated alarm service, but is connected directly to the backstage database where we are saving the monitor point and values and all the data and all the alarms that are produced by the integrated alarm system. The web server that is in charge of preparing and giving the data, let's say, to the operator GUIS running in the browser, and is also accepting commands from the operators for the ones who are allowed to do that. So the commands like acknowledge an alarm or shelve an alarm, that must be done by operators. Okay, we have done also a workshop together with operators and engineers. We wanted to shape basically the GUIS that we needed. I just put one here. This has been developed by INRIA Chile, and this represents the Alma technical building, and this instead represents the Alma operation site building. So basically the red nodes that I have shown you before will not be mapped into boxes, but in GUIS more sophisticated like that. We will have also some GUIS that are geolocalized if we need to tell the operator where in which antenna exactly and where in which pad is the antenna that is failing, for example, or what is the position of a server in a control room or things like that. Okay. So in conclusion, so the project is pretty young, is still under development, is released under LGPL and hosted in GitHub right now. The first version, very, very basic, will be installed in January in the Alma control room, and we have the target to have the new alarm system in operation by the end of 2018. That's it.
Thank you, Alessandro.
Hi, Alessandro. Nice presentation. I do not understand why we cannot just do a little software in Alma Common Software, based in Alma Common Software, just to send the alarms to the central system and then use only that. So
okay, the Alma
what are
Common...
the technical details that why it's not suitable
okay.
ACS for that?
Okay, no, the problem is that we are monitoring more software system, not only the ACS part, let's say. So the power plant is, for example, is running in another monitored system, and there are no connection. Even the network, we cannot access one from the other. So this is the first point. The second point is that the Alma Common Software is not running all the time. It's not running 24/7. So if we tie the alarm system to the Alma Common Software, when the Alma Common Software is not running, you are also losing the alarms from the power plant. So we need something that is more high level than that. But the integrated alarm system is able to get the alarm produced by the common software and show to the operator.
Well, I got it first. Just a rapid question, a fast question. Did you consider any of the alarm system standards existing, like the IC, SCA mentioned that they are applying the alarm system standard for the process industries?
We have done a little survey, but we have not found anything that could fit with our needs. That is why we are getting.
Okay. Then I would have a second fast question. Which latency you have? Because
which?
Latency.
It's a little bit too early to say. In principle, the requirements we have is that the alarm system should be able to deal with the 50,000 monitor points and alarms and present to the operators the result in 2 seconds at the latest from the moment when the problem happens in the hardware or is detected in the monitored control system.
Okay, thanks.